Suppose we want to take the limit of some function in this form, where I have a function raised to a power, where the power is a function. And so this could lead to different types of forms. As x goes to a, I might get some sort of 0 here and 0 in the exponent, or 1 here and 0 in the exponent, and so forth. And I need to determine whether those are indeterminate or not. If they're not indeterminate, then I write the answer down. If they are indeterminate, then I try to somehow convert it to use L'Hopital's rule. So let's look at this one first. What if my limit is going, this base is going to 0 and the exponent is going to 0? Is that indeterminate? Well, we figure that out by just thinking of what each one would do by itself. If I have 0 to some power, ignore the power being 0, but if I have 0 to some power, well, that's supposed to give me 0. So when I have a 0 to the 0, this part is trying to make it 0, because 0 to any power should be 0. But what if I have something with a power of 0? Well, we know that that's defined to be 1. So something to the 0 power should be 1. Well, there it is. Those are indeterminate. They're not pulling in the same direction. One's pulling it to 1, the other one's pulling it to 0. So if this limit ends up being of this form, 0 to the 0, that's indeterminate. What about 1 to the 0? Well, this time, if I have 1 to a power, that's trying to make it 1. If I have something to the 0 power, that's trying to make it 1. That's not indeterminate. That is going to go to 1. If you have something here where it's 1 to the 0, then that answer is 1. Let's try this one. Infinity to the 0, is that indeterminate? Well, infinity is trying to any power, is trying to be infinite. If you have something that's getting huge, a base that's getting huge, it's 1 million, then it's 2 million, then it's 3 million. The power is not going to matter, right? As long as you have a positive power, that's going to try to go to infinity. But again, this is trying to go to 1. Anytime you have a 0 power, it's going to 1. These are not going in the same direction. So this would be indeterminate. So these two are indeterminate. If I had something going, the base going to 0 and the exponent heading to infinity, this is obviously trying to make it 0. An infinite power on something, that does depend. If what you have the power on is less than 1, it turns out that will push it to 0 and they'll actually work in the same way. But if it's bigger than 1, then this is trying to make it infinite. So they could be working the same, but in some instances, this will be indeterminate if the base is bigger than 1. So this one could be indeterminate. Has to be dependent on what you're looking at. What about this last one I've got listed here? And there are other combinations. These are the ones that I'm putting down. Well, the base infinity, something that's getting huge to a power, is still trying to be a huge number, and a huge power on something is trying to make it huge. So these are working together. So this one's not indeterminate. So you got to just kind of go through that analysis when you have a situation like this to determine if it is indeterminate. Then once you do, can I apply L'Hopital's rule? That's what I'm going to work through. So let's look at this one. As x is going to 0, I get 1 in this from this part, so the base is going to 1, and I get infinity from that part. So I get a 1 to infinity, which was not in my list above, but I got to determine, is this indeterminate? Well, that's trying to make it 1, and this exponent, because I've got 1 plus something all the time, this exponent would be pulling it to infinity. Something bigger than 1 is that if the power gets bigger and bigger and bigger, it will go to infinity. So these are not pulling in the same direction. So this is indeterminate. But how do I apply L'Hopital's rule with something like that? I have to manipulate it. Remember, L'Hopital's rule only works for these indeterminate forms. And so what I do here is I'm going to pretend I know the answer is L. It's the limit as x goes to 0 from the right is 1 plus x to the 1 over x. So I'm going to assume that's the answer. And then my issue is I've got this thing up in the exponent. Well, anytime you want to manipulate something out of the exponent, you use logarithms. So I'm going to take the natural log of both sides. And this is what I get when I do that. So I would like to take this 1 over x out of the exponent, but this natural log is outside the limit. The limit's inside of there. But natural log is a continuous function, so that limit can be brought out. And you can say this is the limit as x goes to 0 of natural log of 1 plus x the 1 over x. We're using continuity. That the definition of continuity essentially means that limits can be brought inside your function. And so you could skip straight to this step every time when you have an indeterminate form that involves exponents like this. I just want to be formal on this first one. And now this 1 over x, using properties of logarithms, this will come out in front of that natural log. So this is the limit as x goes to 0 of 1 over x times natural log 1 plus x. And what happens is this typically turns it into this indeterminate form. You get infinity from this, because you're going to have a 0 in the denominator, and you get natural log of 1. This is heading to natural log of 1, and remember your graph of natural log. If you're heading to 1, then natural log is going to 0. And so, it's not divided by, times 0. So it gives me that indeterminate form. When you get rid of that exponent, that's usually what's going to happen with your expression. And we know how to handle that one. We need to flip one of these over into the denominator. Well, there's one screaming to be flipped over. 1 over x flipped over is x, and that then goes in the denominator. Or simply pull it over into the denominator, right? You could write that as a fraction without thinking of flipping it. But now, we already know that as x goes to 0, we get natural log of 1. That's going to give me 0 from the top. Natural log of 1 is 0, and 0 from the bottom. And now I can use L'Hopital's rule, because it's of the right form. So this is the limit as x goes to 0. Derivative of the top is the derivative of 1 plus x divided by 1 plus x. So be sure you use the chain rule correctly. Derivative in the bottom is 1. Well, so that's just the limit as x goes to 0 of 1 over 1 plus x. And now letting x go to 0, I get a 1. That's not my answer, right? Because if I work my way back through here, that's actually natural log of L is 1. But looking right above that, I need L, not natural log of L. So I have to get back to L, which means I have to exponentiate both sides of this. So on this side, cancels out. So the actual answer is E. So got this weird thing going on where one of them's trying to make it infinite, one of them's trying to make it 1, and they end up at E. So E is that weird number that just shows up a lot in mathematics. Let's do a second example just to go through that process again. Here we go. We got something raised to a power where that base is going to 0 and sine of 0, so the numerator is going to 0. And we did talk about, the exponent's going to 0. And we talked about it. A base of 0 is supposed to be 0, an exponent of 0 is supposed to be 1. That's indeterminate. Got one pulling the 0, one pulling the 1. And so we will do this like we did above. I need to get that sign out of the exponent, so I'm going to pretend the answer is L. And then I can take the natural log of both sides. So natural log of L equals natural log of all of this, but as I said in the previous, we're just going to skip the step and pull that limit out of the natural log by continuity. So we'll go straight to that. And that allows me to pull the sign out in front using the properties of logarithms. And what will happen at this step every time is you're going to get this 0 times infinity form somehow. You're going to get a 0 times infinity. That form I cannot apply L'Hopital's rule to, so I need to flip one of these into the denominator. And usually if it's a trig function, that's a better bet than a logarithm, because a trig function has a name when you flip it over. So this is going to flip over and become 1 over sine x, and I'll stick that in the denominator. But that's the same as saying cosecant. So I got natural log over cosecant. And this one is now going to infinity, because remember, natural log looks like that. And so as I come into 0, it looks more like that. But anyway, as I come into 0, it is going to minus infinity. And cosecant, which is 1 over sine, is also going to infinity. It's positive infinity. It doesn't matter if they're different infinities. It's still an infinity over infinity form. And that's a form I can apply L'Hopital's rule to. Derivative of natural log is 1 over x. Derivative of cosecant is minus cosecant cotangent. And as x goes to 0, well, I'm probably going to change this to sines and cosines. It's going to be likely my best bet. So I'm going to take the limit as x goes to 0 from the right. Let's see, down here, before I start, well, just leave this 1 over x for now. This is going to be 1 over sine and cosine over sine. So I'm going to have minus cosine over sine squared. And so when I flip this around and multiply, I get the limit as x goes to 0 from the right. In the bottom, I'll have x times cosine, and the top left sine squared. All right, so now as we go to 0, you can see I've got the bottom going to 0 because of the 0 here, because of the x, and the top going to 0. So this is 0 over 0, but it's sort of like one of the problems previously. The cosine is not contributing to that mess. So I can extract that away from that limit and just deal with 1 over cosine separate from sine squared over x. So this part I can do. This part's going to require L'Hopital's rule. So this part I can see is still a 0 over 0 form. This is going to give me 1. So I'm not going to write the step, but I can take the limit of that and the limit of that separately. And when I do that and apply L'Hopital's rule to the second one, I get 1 from this limit because it's 1 over cosine of 0. But the second one is where L'Hopital's rule is being applied. I get the limit as x goes to 0. Derivative of sine squared is 2 sine times the derivative of sine, which is cosine. And the derivative of x is 1. So finally, I've got it. Because as x goes to 0, I no longer get a 0 in the denominator. I get 0. And so remember, that's not the answer. That's natural log of L is 0. To get back to L, I take e of both sides and tells me that L is 1. So the original limit here turned out to be 1. So in some sense, the exponent won this race.